Greetings everyone, I'm delighted to present our work titled An Autonomous Serverless Fuzzy Logic-Based Decision Support System for Evaluating the Reliability of a Country's Electric Power System, authored by Professor Anatoly Melnik and me, Bogdan Zimchenko. Let's commence by understanding the broader context. Electric power systems, the lifelines of modern societies, are exceptionally complex. With a multitude of interdependencies and variable conditions, managing these systems and evaluating their reliability becomes challenging. Numerous factors can influence the trustworthiness of energy provisioning systems, such as energy production, usage patterns, climatic conditions, upkeep levels, human errors, and constraints in the transmission network. A thorough evaluation method that considers each of these aspects is required to effectively assess the reliability of EPS. Our research hence serves as a vital leap forward. We've designed an innovative solution to ensure a more resilient power infrastructure for countries. Azure offers many benefits that align with our goal to assess the dependability of electric power system using the Decision Support System or DSS. This includes scalability, cost efficiency, high availability, and robust security. Our Azure-based DSS structure has key components: AP gateway, controls, secures and monitors AP functions, safeguarding data integrity, receiver function, and HTTP-triggered Azure function, processes incoming data and deposits it into Service Bus. Service Bus is a message queue system, improving scalability and fault tolerance. A fuzzy logic function extracts data from the service bus for processing using fuzzy logic techniques to calculate reliability indices. Cosmos DB stores calculated reliability indices, input data, and fuzzy rules, facilitating easy querying for analysis. Azure Blob Storage stores a initialized fuzzy inference module instance to improve system efficiency. AP function fetches latest reliability data from Cosmos DB, providing an API for external access. Here is a diagram of the relational database for storing data reference to fuzzy logic. The fuzzy logic area's table record has an area name property that corresponds to the topic area it solves. A term table record has a term name string property that represents a linguistic variable. A term table stores a set of linguistic variables for a particular subject. The sets table record has a key string property, which is a linguistic value that can be applied to the corresponding linguistic variable, and its numeric value, which is the value double property. A rule table record has a rule value string property that represents a rule in a specified format using a linguistic variable and its corresponding linguistic value. Rules are defined as if-then constructs. The EPS Reliability Database stores country-specific and region-specific data as well as EPS reliability values. This relational database is designed to accommodate a variety of geographical areas and their respective reliability values, thus allowing for a broad and detailed assessment. Let's delve into our fuzzy logic implementation. We start with defining linguistic variables for various parameters. This include power generation, power consumption, air temperature, sunlight intensity, maintenance status, and weather status, alongside an output variable for the reliability index. Once the linguistic variables are defined, a fuzzy rule base is created. The fuzzy inference mechanism evaluates these rules to determine the degree of each rule's fulfillment. We use the centroid method for the defuzzification process, which calculates the crisp output value as a center of gravity of the fuzzy output set. This entire mechanism is implemented using the aforge.net framework. We've assessed the proposed system using simulated test data mirroring real-world parameters like power generation, consumption, temperature, sunlight intensity, and weather conditions. This test data, focusing on various regions in Ukraine, was developed using historical data, trend analysis, and statistical models. Upon generating this data, it's sent to the data receiver function for validation and transformation, then stored in the message queue. The fuzzy logic function retrieves and processes the data to compute the reliability index for different regions, which is stored in Cosmos DB. Users can access the most recent reliability data through the API function, enabling them to understand the reliability of the electrical systems easily. Let's talk about the results. We generated a heat map diagram displaying the EPS reliability rating for various regions throughout the day. This visual representation helps in identifying trends, patterns, and potential concerns related to the EPS's reliability, providing an intuitive tool for experts in the field. Looking forward, we aim to refine our fuzzy logic model by incorporating additional parameters and exploring machine learning techniques. We plan to develop a hybrid architecture addressing data privacy, security, and latency concerns. And importantly, we aspire to evaluate our system using real-world data, comparing it with traditional approaches for a robust analysis. Our autonomous serverless GSS on Azure offers scalability, flexibility, and cost efficiency, removing the need for local hardware. It employs fuzzy logic for robust decision making with uncertain inputs, ensuring reliable EPS evaluations. Integration with existing infrastructure is seamless, and Azure's security measures safeguard data. Our system supports continuous improvements and future enhancements. Research shows the framework's potential in reliable EPS assessments, with heat map visualization providing clean regional insights. Our unique blend of serverless architecture and fuzzy logic marks a novel approach in EPS reliability assessments. But it's worth noting that model precision hinges on the quality of input data, and fuzzy rules and cloud's resilience raises potential security concerns. Thank you for your attention and feel free to ask any questions.